strongly continuous and analytic resolving families of operators for fractional differential equations in Banach spaces. Firstly, I want to recall definition of Riemann-Liouville fractional integral, Riemann-Liouville fractional derivative, and the Hilfer fractional derivative. It has this form. It is some interpolation between the Riemann-Liouville fractional derivative and the Gerasimov-Kaputov fractional derivative with parameter beta of interpolation. And we will use such definition of the Hilfer derivative, regularized form of this derivative, analogously to the regularized form of Gerasimov-Kaputov derivative. And by the Hilfer derivative, we will call this construction. And for negative alpha, we will define Riemann-Liouville fractional derivative of the negative order is the Riemann-Liouville fractional integral of the order minus alpha. And we see that for Hilfer derivative with two parameters, if parameter of kind beta is equal to 1, then we will obtain Gerasimov-Kaputov fractional derivative, and if parameter beta is equal to 0, then we will obtain Riemann-Liouville fractional derivative. We know that for first order differential equations in Banach spaces, theory of resolving semigroups is developed very well, and we know that there is a Hille-Yosida theorem on the conditions of such operator A for the existence of C0 continuous semigroup of this equation. And this semigroup, every operator of this semigroup is operator which maps initial value into the value of a solution at the point T. And if we have a semigroup, then the Cauchy problem for equation 1 is uniformly well posed, and we can study linear inhomogeneous equation of the corresponding form, and a solution of such equation can be represented using operators of resolving semigroup. And besides, we can research semilinear equations of the form 3, and the Cauchy problem for such equation can be reduced to this integral equation, and we can investigate such equation using fixed point theorem, contraction mappings, and so on, and we can establish local unique solvability and global on the given segment unique solvability, and so on. If we have an equation with some fractional derivative, maybe not Riemann-Liouville, another form of the derivative, maybe Gerasimov-Kaputov, Hilfer, and so on, then we can consider the notion of resolving family of operators. Such operator maps the initial value of the initial problem into the value of a solution of such problem if other initial values is equal to 0. Higher initial values is equal to 0, and lowest is arbitrary. And such family of operators we will call resolving for equation 4. And we can construct a solution of such equation. We can study linear inhomogeneous equation, and a solution for such equation will, under some conditions on the function f, will have this form where S is resolving family of operators, and here delta depends on the kind of fractional derivative. And also we can consider quasilinear equation with the highest derivative, fractional derivative, and the lower fractional derivative of the orders alpha 1, alpha 2, and so on, alpha n. And an initial value problem for such equation can be reduced to this integral differential equation, and such equation can be studied by methods of fixed point theorem, for example. Some references in these famous books, Hille-Phillips, of Hille-Yosida, and in the, for example, this work of Mikhail Zosimovich Solomyak, theory of semigroups of operators was developed, and I said that such theory has many applications for the consideration of first-order differential equations in Banach spaces, and with application to the initial boundary value problems for partial differential equations. In this work, linear integral differential equations in Banach spaces are studied also in terms of resolving families of operators. Jan Pruss study resolving families of evolutionary integral equations in Banach spaces. Emilia Bazlekova investigated resolving families for fractional differential equations in Banach spaces with Gerasimov-Caputo derivative. We will consider here the Cauchy type problem for this equation with Hilfer derivative, the order of the derivative alpha, and the kind of this derivative is beta. Operator A is linear and closed, unbounded, generally speaking, and these are initial conditions. And we have the so-called Cauchy type problem when we have Cauchy problem not for the function z, but for the fractional integral of a solution, fractional integral of this order. And a family of operators is called resolving for equation 7 if the next conditions are satisfied. Firstly, this family is exponentially bounded and has a power singularity at 0 point. This family is strongly continuous, and this condition is fulfilled in 0 point. Operators of the resolving family commute with the operator A in this sense, and such function st on z0 for arbitrary z0 from the domain of operator A is a solution of the Cauchy type problem with arbitrary first initial value and 0 values in other conditions. Here we used the notion of a solution of problem 7-8. Here we wrote the definition of a solution. A solution is understood in the classical sense. It does all the derivatives, fractional derivative in the equation and in initial conditions must be continuous, briefly. And note that if operator A is bounded, the resolving family of operators for equation 7 has the form of Mittag-Leffler function. We can obtain it easily. Such Mittag-Leffler function. Define a class of operators, operator linear enclosed in the Banach space Z is called the operator of the class C alpha beta omega for some constant, non-negative constant omega if the following two conditions are fulfilled. If lambda belongs to such half plane, then alpha degree of lambda belongs to the resolving set of operator A. And there exists such constant such that for every lambda from this half plane, right half plane in the complex plane, and for all natural n and maybe 0, and we have such inequalities, usual derivative of the order n of this expression, and here we have gamma function and powers of this expression. And if we take alpha is equal to 1, then m will be also equal to 1. Then we will obtain here derivative of usual resolvent, lambda minus a minus 1. And here we will obtain factorial and usual power n plus 1. And so these conditions will have the form of Hille-Yosida conditions in the theorem of Hille-Yosida. Moreover, if we will take beta is equal to 1, beta, but alpha is arbitrary, then we will obtain the conditions for such of this form, which were constructed by Emilia Bajlekova for the theorem on generation of resolving families for equation with the Gerasimov-Caputo derivative, if beta is equal to 1. If beta is equal to 0, then it will be conditions for equation with Riemann-Liouville derivative. It was obtained firstly by Alexander Vasilyevich Glushak in some cases, and recently we will obtain some kind of results for arbitrary alpha, and we can prove such statement that this class of operators lies in the class of operators for Gerasimov-Caputo derivative, and we see that this class may be wider than this class for other beta not equal to 1. We will later discuss this situation. And another interesting result, such result is known for example, for Gerasimov-Caputo derivative. If A belongs to this class, for alpha is greater than 2, then A is bounded operator. Hence, we need to consider only the case alpha not greater than 2, and it is known that for the obtaining of such results, necessary and sufficient conditions on an operator for the generating of resolving family, and even in the case of semigroup and the case of first order equations, direct statement of such theorem is the proof of such statement is simple, since if there exists resolving family, then we can obtain Laplace transform of this family, and we will prove that operator A belongs to this class. But the inverse assertion is essentially more difficult, since if we have this operator and we have such its resolvents, we cannot use inverse Laplace transform directly. It can be made only in Banach spaces with Radon-Nikodym properties, but in arbitrary Banach spaces it is not possible, even in the case of the first order equations. And in the theory of semigroups of operators, we use for the proof of the existence of resolving family, we use various approximations of the C0 continuous semigroup. And in the case, we will use such kinds of approximations of Phillips type, since it is based on the Phillips inversion formula. Here, H beta, this function, this is the derivative of this function of the Kath order, and we can obtain such estimates for these operators, and the strong limits of these operators will be operators of the resolving family, and we need to prove it. We will not to do it now, but it is not the proof is not small, but we will formulate. Let alpha not greater than 2, beta from this segment 0, 1, then there exists a resolving family of operators for equation 7, if and only if A belongs to this class. In this case, operators of the resolving family have the form of strong limits of these approximations from the previous slide. And using such result, we immediately can obtain this corollary. It is the case of alpha not greater than 1. Then we have such initial condition, and there exists a solution of the equation 7, and its solution has this form. And for alpha from this semi-interval 1, 2, then for arbitrary initial values and such Cauchy problem for equation 7 has a solution, and the solution has this form. We will discuss also analytic resolving families. We will denote this sector with the semi-angle greater than p divided by 2, and this sector in one complex plane, and another sector with smaller angle in the complex plane of t. A resolving family of operators is called analytic if it extendable analytically on a sector of this form. An analytic resolving family has this time for some psi 0 omega 0 delta, if for any psi not greater than psi 0 omega greater not less than sub-0 omega greater than omega 0, there exists a constant such that for all t from this smaller sector, this inequality is valid. Denote a class A alpha for some theta 0 omega 0, a set of all operators linear and closed such that for every lambda from this from such sector is a wider than half plane in the previous considerations. We have alpha degree of every such lambda must belong to resolving set of operator A, and for any theta and omega, there exists a constant k such that for all lambda from this smaller sector, this inequality is valid. We see that in contrast to the case of the strongly continuous semigroup, here we need to obtain only one inequality, not countable number of inequalities. And also we see that this class does not depend on the parameter beta. We will use such denotation, and if alpha is greater than 0 and beta from this segment, then there exists an analytic resolving family of such type for equation 7 if and only if operator A belong to this class. It has operators of the resolving family have this form where contour gamma maybe it can be taken as a boundary of sector S theta omega with plus constant and positive constant. We see that here we have beta, but the class of operators does not depend on beta. And we will see that even for other fractional derivatives, we will obtain the same class of operators, which depends only on the order of the fractional derivative. In the proof of this theorem on the generation of analytic resolving family, it can be called generalization of Hille-Yosida's theorem. The key role in the proof plays this theorem, Sava type theorem. If we take here delta is equal to 0, then we will obtain a theorem of Miroslav-Sava. This theorem describes the Laplace transform of a function which analytic in some sector, containing positive semi-axis. If we have a theorem on the existence of resolving family, we will obtain a theorem on unique solvability of linear and homogeneous equation. And the main question, what conditions we need for such theorem? And if we will take such lambda, beta, A from this class, Z0, Z1, and so on, Zm-1 belongs to domain of A, and F is continuous in the graph norm of operator A, or Hölder continuous in the usual norm in the Banach space. Then this function is a unique solution of problem 8-9. And here we see that we use only resolving family of operators. Here we take Riemann-Liouville integrals of the integer order, and here we take Riemann-Liouville integer not integer, Riemann-Liouville fractional integral in the case of m is equal to 2, and Riemann-Liouville fractional derivative if m is equal to 1 of the resolving family. We can obtain also perturbation theorem for the class of A alpha. And here we see that for some classes of subordinated operators of B with some conditions, the sum of operators A plus B belongs to the class A alpha, maybe with other constants. And if B is linear and bounded, then all these conditions is fulfilled, and this sum will be of this class if operator A from this class. This class A alpha is also called class of sectorial operators. In the theory of semigroups of operators, when alpha is equal to 1, in several monographs, this class is called sectorial, and we will use this term further for arbitrary alpha. Sectorial IDS belongs to such class. And now we will consider another fractional derivative for a finite sequence of numbers from these semi-intervals from 0 to 1, we include. We define the Dzhrbashyan-Nersesyan fractional derivatives for every set of lambda. We have such fractional derivatives. Here, alpha 0, we have only Riemann-Liouville fractional integral if alpha less than 1, or identical operator if alpha 0 is equal to 1. And for other cases, we will take Riemann-Liouville fractional derivatives, and on the last place we have Riemann-Liouville fractional integral or identical operator, since here we have alpha k minus 1. Here there are references on the work of Dzhrbashyan and Nersesyan where they studied Cauchy problem, but it is not maybe Cauchy problem for differential equations of fractional order, such fractional differential equations with such fractional derivative. And this work was published once again in this journal, Fractional Calculus and Applied Analysis, in 2020. And the special cases of the Dzhrbashyan-Nersesyan derivative are all the mentioned today fractional derivatives. For example, if we need to take Riemann-Liouville fractional derivative, we will take these numbers alpha 0, alpha 1, and so on, alpha m will be so alpha minus m plus 1 and units m times. The Gerasimov-Caputo fractional derivatives m units and alpha minus m plus 1. And the Hilfer fractional derivatives, this number m minus 1 units and this number. And we also use such notation, sigma k, it is sum of alpha j from 0 to k minus 1. And we will consider this equation with the Gerasimov-Caputo derivative, alpha m, endowed by the Dzhrbashyan-Nersesyan initial conditions. They are called these conditions Cauchy conditions and Cauchy problem, but these conditions have this form. Here we take Dzhrbashyan-Nersesyan fractional derivative, and last of numbers is alpha k, and here k, and we need to take k for every k from 0 to m minus 1. A solution of this problem is such function. Here it is wrote, it is classical solution of such problem. A family of operators is called resolving for equation 11 if the next conditions are satisfied. Operators satisfy this inequality, exponentially bounded, and there is a singularity in 0 point if alpha 0 less than 1. The family of operators is strongly continuous. Operators commute with the operator A. STZ0 is a solution of such problem where in the first condition we have arbitrary element from the domain of operator A, and in other condition we have zeros. If A is linear and bounded operator, the resolving family of operators for equation 11 has the form of Mittag-Leffler function. It is the result of Dzhrbashyan and Nersesyan from the mentioned article, and here we see that this function depends only on the order of the equation, sum of all alpha k minus 1, and on alpha 0, and does not depend on other alpha k. And operator A is called the operator of such class for some constant omega if the following conditions are fulfilled. The sigma m degree of this half plane belongs to resolving set, and we have such inequalities, and here we can take the set of alpha k of such forms, and in every of cases we will obtain the conditions for corresponding classes of the operators for equation with the Riemann-Liouville fractional derivative, Gerasimov-Caputo fractional derivative, and the Hilfer fractional derivative. If we take these conditions, they are Hille-Yosida type conditions. And we have also this embedding. And it is known, it is proved this result that E is greater than 2, then, and operator A from this class, then A is bounded. And as in the previous case, we can construct approximations of Phillips type, and we'll prove that strong limits of such approximations will give operators of the resolving family. And we have this main result, generalization of the Hille-Yosida theorem. If alpha k from these semi-intervals and this condition is satisfied, then there exists a resolving family of operators for equation 11 if and only if operator A belongs to this class. In this case, these operators are strong limits of the approximations. And as corollary, we will obtain that for every initial values in the in conditions 12, there exists a unique solution of problem 11-12. The solution has this form, and here we see that we have a resolving family of operators which depends only the sum of all numbers alpha k and of alpha 0, but using this formula we will obtain every initial condition with every set of alpha 0 and so on alpha k. And analytic families of operators and the class of generators of an analytic resolving family is the same for other fractional derivatives, but here we have order of the derivative of sigma m, and for operator m from the same class a sigma m as before it was called sigma alpha with number alpha. Here it is sigma m. Then we define such operators for every positive t and every real beta. And we will use such operators in the next theorem. We can consider that the resolving family of operators, analytic resolving family of operators here, will be such operators: sigma m minus sigma 0 minus 1. If we take beta is equal sigma m minus sigma 0 minus 1, we will obtain analytic resolving family of our equation 11. And in the linear inhomogeneous equation has such theorem of unique solvability. If these conditions are satisfied, this inequality lambda 0 plus lambda m is greater than 1 is the same as in the work of Dzhrbashyan-Nersesyan, and this condition arises in the proof, and without it it is impossible to prove our statements. And operator A from this class, sectorial with such parameter, zk from the domain of operator A, and f from f is strongly continuous in the graph norm of operator A, or Hilfer continuous in the usual norm. Then problem has a unique solution. It has this form, and here on the first place we have resolving family, and other expression will be fractional integrals or fractional derivative here of the resolving family. But if we will write it in terms of these operators, we will obtain such a representation. And I note that these class of functions which are continuous in the graph norm or Hilfer continuous in the usual norm are the same as in the semigroup theory. It is known that in the semigroup theory, if we will consider linear homogeneous equation with a sectorial operator, then for such functions f, we will have analogous result and analogous formula, Duhamel formula. And I will consider an example in the space of sequences L2. This example illustrates maybe a difference between various classes of operators and difference and other things. And let sigma m from this semi-interval, gamma from this semi-interval, an unbounded monotonically increasing sequence of positive numbers, mu n. Consider the Cauchy type equation. We have a sequence of sets of initial values and sequence of equations. But if we will consider this problem 1314 in the space L2, then we will have a problem 1112 with the Dzhrbashyan-Nersesyan derivative. We will define operator A gamma such that it is defined on such elements of L2 that this sequence belongs L2 also. Such elements will make up the domain of this operator. Operator is a multiplication. Every element of the sequence multiplied by a number mu n multiplied by exponent. And these numbers are situated in the complex plane on the semi-axis from 0, and this semi-axis is with angle with the positive semi-axis. Angle is p gamma divided by 2. And so gamma is a parameter. We will variate this parameter. And it is easy that such operators is linear enclosed, and spectrum of such operators are these numbers. And we will take p omega sigma m as a sigma m degree of half plane such set. And for gamma from this interval, we have that sigma of A gamma, this set, with intersection with this sigma m degree of half plane is not empty. And so the first condition of the definition of operators from this class is not does not fulfilled. Therefore, A gamma does not belong to this class for such gamma between minus sigma m till sigma m, not including them. For gamma from such class, it does modulo of gamma is greater than sigma m. We can solve for every fixed n such problem, as it is solved in the article of Dzhrbashyan and Nersesyan, and we will obtain such solutions. And so if the resolving family of operators exists, then it must have such form where every initial sequence of initial values multiplied it by such numbers for every n various multiplicators, multipliers. Since we have such using approximation of the of this Mittag-Leffler function with fixed t and with n tending to infinity, we will obtain that such numbers are similar to this. And here we see that this operator is these operators for every fixed t is a bounded operator. Therefore, we can show that a gamma belongs to this class. Moreover, it can be shown that a gamma belongs to the class of sectorial operators where angle theta 0 is equal to this one, pi divided by 2, 1 plus modulo of gamma minus alpha. And it was if gamma is equal, is greater, modulo of gamma greater than sigma m. And it remains to consider gamma is equal to plus minus sigma m. Let it be plus. We will consider such numbers, and for a fixed t and with n tending to infinity, we will obtain such behavior of this sequence. And we see that if alpha 0 is less than 1, then this sequence is infinitely increasing. So these operators S sigma m are not bounded, and operator A sigma m does not belong to this class if alpha 0 less than 1. If alpha 0 1, that here we will have 0, and then such operators will be bounded, and we will have resolving family of operators of such equations if alpha 0 is equal to 1, and here gamma is equal to sigma m. And A sigma m will belong to this class with 1 on the first place. So we have very many sectorial operators for every gamma from such intervals, and many operators which are not generating resolving families, and some operators which strongly continuous but not analytical. In the case of sigma m is equal to 1 and alpha 0 is also equal to 1. And if we will consider in the bounded domain with a smooth boundary problem for equation which can be interpreted as equation of ultra-slow dynamics of non-relativistic systems of this form. It is similar to linear Schrödinger equation, but here we have Dzhrbashyan-Nersesyan derivative. It is boundary condition, and they are initial conditions. We can choose that Lebesgue space operator A of the form of imagery unit multiplied by Laplace operator on V, and with the domain we have boundary zero boundary condition. This condition belongs to the domain of operator A, and zk will be is equal to functions uk from this domain, and function for every t will be element of this Lebesgue space. And we have spectrum of operator A here. It will be a sequence I multiplied by lambda n, where lambda n negative sequence tending to minus infinity. Phi n are eigenfunctions which correspond to eigenvalues I lambda n. Take Zn as Fourier coefficients of u, and every function u will be a sequence of Fourier coefficients. And moreover, every function will be a sequence from the space L2, small l here. And we see that we by this way, we will reduce our problem 15-17 to the problem 13-14. And here, this operator A will be operator A minus 1. It is gamma is equal -1. Since these numbers will be directed along the negative imagery semi-axis. And we already know that such operator belong to the class of sectorial operators with such parameters. If sigma m is less than 1, sigma m is defined by these numbers. It's sum minus 1. And if sigma n is equal to 1, then A minus n belongs to this class, only generators of strongly continuous but not analytic resolving families. If lambda 0 is equal to 1, otherwise it will be, this operator will not generate even strongly semi-continuous family of operators. And if lambda 0 less than 1 and sigma n is equal to 1, or sigma n greater than 1, then A minus m also will not generate strongly continuous resolving family of operators. And here we can, I see that my time is almost over. Several words. Here we can consider initial boundary value problem for the system of linearized fractional Boussinesq equations. And here we have Hilfer fractional derivatives, equation of уравнение несжимаемости, забыл. And three equations. These two equations are for vector valued function v, and the next, the third equation is for scalar function. Theta is scalar function, v is vector valued function. We will choose spaces and operators, and will reduce our our system to the system of equations. These equations will belong to the domain of operator A, and we will obtain a system of equation with such matrix operator, and we reduce our system to our abstract initial value problem for equation in a Banach space with such operator A in this space Z. And then we can obtain that this operator A is sectorial with some parameters. Here it is a proof of this fact. Using this sectoriality of A, we can use theorem on unique solvability of the linear inhomogeneous equation with a sectorial operator with a Hilfer fractional derivative, and we will obtain this theorem. And in the case of lambda, it was for lambda between 1 and 2, and if lambda between 0 and 1, we will obtain similar result. And here several works about strongly continuous, about the generation of strongly continuous resolving families, and here for analytic resolving families, and here also with various fractional derivatives, and maybe with the distributed fractional derivative similar result in these works with a distributed fractional derivative of distributed Gerasimov-Caputo derivative or distributed Riemann-Liouville derivatives, and multi-term equations in this form, and for quasilinear equations with linear path of the considered form. Several results. The work was supported by a grant of Russian Science Foundation. Thank you for your attention. Thank you very much.